Hello there and welcome back to the Sleep Science. Tonight you're floating, no rocket required, just drifting in the velvet dark between galaxies, where starlight thins into a faint silver mist and the universe feels less like a place and more like a question. Somewhere out there, beyond the quiet blink of satellites and the patient spin of spiral arms, something has appeared that absolutely should not exist. And yet here it is, glowing stubbornly in the data like a typo in the laws of physics. You probably won't survive this. Not because it's dangerous, relax, but because if the measurements hold up, the comfortable story you learned about how the cosmos formed might need a serious rewrite. And rewrites on that scale tend to bruise a few egos. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And while you're settling in, tell me your location and local time. I love imagining this little constellation of listeners scattered across the globe. Some of you under midnight skies, some sneaking this in during a suspiciously long bathroom break at work. I see you now. Dim the lights. Maybe turn on a fan for that soft background hum. And let's ease into tonight's journey together. You're standing in a control room that smells faintly of warm circuitry and coffee that's been reheated one too many times. Screens glow in the dimness. Data streams in numbers, wavelengths, redshift values, ordinary cosmic chatter until it isn't. A signal arrives from deep space. Not a pulsing alien greeting, sorry, but a smear of light so distant that it left its source billions of years ago. Astronomers measure its redshift, the stretching of light caused by the expansion of the universe. Since Edwin Hubble's observations in 1929, we've known that galaxies are racing away from us, their light shifting toward the red end of the spectrum like a cosmic Doppler effect. That's mainstream textbook stuff. Expansion equals redshift. Redshift equals distance. Distance equals looking back in time. Simple, elegant, comforting, except this object's redshift suggests it formed just a few 100 million years after the Big Bang. For context, the universe is about 13.8 billion years old, a figure refined by measurements of the cosmic microwave background radiation, first detected accidentally in 1965 by Arno Penzias and Robert Wilson, who were just trying to fix a noisy antenna and instead stumbled onto the afterglow of creation. Imagine discovering the origin of everything because you couldn't get rid of static. That's either inspiring or deeply unfair. So you look at the timestamp. Early universe, baby cosmos. The cosmic equivalent of a toddler still figuring out object permanence. And yet the light coming in suggests something mature, structured, massive. Like finding a fully grown oak tree in a pot where you planted a seed last Tuesday. At first, the team assumes it's a calibration error. Telescopes are sensitive creatures. They sulk when dust settles on mirrors. They complain when software updates go sideways. The James Webb Space Telescope, launched in 2021 and stationed nearly 1 million miles from Earth at the L2 Lagrange point, is humanity's most powerful infrared eye. It was designed specifically to peer into this early epoch. If anything could catch a whisper from the dawn of time, it's Webb. And Webb is whispering back, very calmly. No mistake. This is real. You zoom in on the data. The brightness suggests a galaxy already packed with stars, not just a few scattered pioneers, but a bustling metropolis of them. According to standard cosmology, the first stars, population 3 stars, were massive, short-lived, and composed almost entirely of hydrogen and helium. Heavy elements like carbon and oxygen had to be forged inside those stars and spread by supernovae before more complex structures could form. That takes time, explosions, recycling, cosmic patience. But here, in the infancy of the universe, you're seeing signs of complexity that imply multiple generations of stars have already lived and died. It's like arriving at a construction site on day one and finding not scaffolding, but a finished skyscraper with questionable interior design choices. Astronomers have been fooled before, of course. In the late 19th century, some genuinely believed they saw canals on Mars, carefully engineered lines etched across its surface. The Italian astronomer Giovanni Schiaparelli used the word canali, meaning channels, and the world ran with it. Suddenly, Mars had civil engineers. Turned out, it didn't. Just optical illusions and enthusiastic imaginations. So skepticism is healthy, mandatory even, but the numbers refuse to budge. Spectroscopy, the splitting of light into its component wavelengths, reveals chemical fingerprints. The patterns suggest heavier elements than expected for such an early epoch. That's not just a mild discrepancy. That's a cosmic scheduling conflict. Historians still argue whether paradigm-shifting discoveries are accepted because of overwhelming evidence or because the previous generation of scientists eventually retires. Science is gloriously self-correcting, but it can also be adorably stubborn. You lean back in your chair. The universe, according to the prevailing Lambda-CDM model, began in a hot, dense state and gradually cooled, allowing matter to clump under gravity into stars, galaxies, and eventually galaxy clusters. Dark matter, an invisible substance making up about 27% of the universe's energy density, acts as scaffolding, pulling ordinary matter into shape. But this object appears too big, too bright, too evolved for its assigned time slot. It's as if the universe showed up early to its own party, fully dressed, music already playing. And that's the signal. Not a radio beacon, not a flashing light, just photons that have traveled billions of years to tap you on the shoulder and say, by the way, your timeline might be off. You scroll through simulation comparisons. None line up cleanly. The formation rate required to build something this massive so quickly would push star formation efficiency to extremes. Either the early universe was far more industrious than we thought, or something fundamental about our models needs adjusting. Three possibilities hover in the room like polite but ominous guests. The measurements are wrong, the interpretation is wrong, or the universe is weirder than we've allowed ourselves to imagine. You can almost hear Einstein clearing his throat from across the century. For now, the signal sits there in the database cataloged, analyzed, double-checked. A small cluster of photons with an outsized attitude. It shouldn't exist, and yet it does. And you, drifting in this quiet observatory glow, are about to follow those ancient beams of light backward into a time when the cosmos was young, hot, and supposedly far less complicated than this. Supposedly. You swivel your chair toward the instrument responsible for all this cosmic drama, and in your mind you drift outward, far beyond the control room, past the orbit of the moon, past the comforting clutter of satellites to a quiet gravitational balance point nearly 1,000,000 miles from Earth. There, suspended in a delicate dance between our planet and the sun, floats the James Webb Space Telescope. It doesn't look heroic. It looks like a golden, angular insect unfolding in slow motion. Its segmented mirror, 18 hexagonal pieces coated in a microscopically thin layer of gold, spans about 6.5 meters across. That gold isn't decorative flair. It reflects infrared light with exquisite efficiency. Infrared is the key because the earliest galaxies are so distant their visible light has been stretched into longer wavelengths by cosmic expansion. If you want to see the dawn, you need infrared eyes. The telescope launched on December 25, 2021. Yes, Christmas morning, which is either poetic or deeply inconvenient for Mission Control's holiday plans. The launch itself was nerve-wracking because Webb folded up like cosmic origami to fit inside the rocket. Over the next 2 weeks, it executed a complex deployment sequence involving hundreds of single points of failure. Engineers sometimes referred to it, only half-jokingly, as 29 days of terror. If any one mechanism had jammed, humanity's most ambitious space observatory might have become the most expensive piece of abstract art ever placed in orbit. But it worked. The sun shield, 5 thin layers the size of a tennis court, unfurled perfectly, cooling the telescope to around -223 degrees Celsius. Cold enough that its own heat wouldn't drown out the faint whispers of ancient galaxies. You imagine it there now, serene and patient, permanently facing away from the sun like someone politely avoiding eye contact at a party. The L2 Lagrange point where Webb resides isn't a solid location, but a gravitational balancing act. It was first mathematically described in the 18th century by Joseph Louis Lagrange, who worked out that certain points in a two-body system allow a third, smaller object to maintain a relatively stable position. It's one of those elegant solutions that makes you suspect the universe secretly enjoys calculus. And from that perch, Webb stares deeper into time than any telescope before it. The Hubble Space Telescope, launched in 1990, gave us breathtaking images of distant galaxies and famously required a corrective optics mission after a mirror flaw was discovered. That repair, conducted by astronauts in 1993, became one of NASA's most celebrated fixes, a reminder that even billion-dollar instruments occasionally need glasses. Webb, in contrast, was designed without the possibility of astronaut servicing. No pressure. When the anomalous object first appeared in Webb's early deep-field observations, it wasn't alone. The telescope had been surveying patches of sky for faint, high-redshift galaxies, searching for structures formed within the first few 100 million years after the Big Bang. Astronomers expected small, irregular clumps, proto-galaxies still assembling, messy and chaotic. Instead, among the expected faint smudges, this one stood out. Brighter, more structured. A little too confident. You lean closer to the screen. The near-infrared camera, or NIR cam, captured the initial data, Spectroscopic follow-up with NRSpec split its light into detailed wavelength signatures. Redshift values climbed higher than anticipated, placing it astonishingly early in cosmic history. Historians still argue whether revolutionary instruments drive paradigm shifts more than revolutionary ideas. Did Galileo change astronomy because he was brilliant, or because he had a telescope when others did not? It's probably both. Technology and theory dance together, occasionally stepping on each other's toes. The first reaction among researchers is caution. High redshift estimates can be tricky. Dust can redden light. Gravitational lensing, where massive objects bend spacetime and magnify background galaxies, can make distant objects appear brighter and closer than they truly are. Einstein predicted gravitational lensing in 1915 as part of general relativity, and it was confirmed during the 1919 solar eclipse when starlight was observed bending around the sun. That observation made Einstein internationally famous almost overnight. Imagine becoming a global celebrity because your math checked out. So the team checks for lensing distortions. They map foreground mass distributions. They analyze arc shapes and magnification factors. Nothing obvious explains away the brightness. And here's a quirky tidbit for you. Before Webb even launched, some astronomers joke that if it found galaxies too early, theorists would simply invent galaxy inflation to explain it. Not the cosmic inflation that describes the universe's exponential expansion fractions of a second after the Big Bang, but inflation in the sense of, we'll just stretch the equations until they fit. Scientists have a sense of humor. It's just very niche. You picture the telescope patiently collecting photons that began their journey over 13 billion years ago. Those photons have crossed expanding space, dodged intergalactic hydrogen clouds, and slipped past clusters of galaxies, all to land on a golden mirror and trigger a detector pixels smaller than a grain of sand. If photons had loyalty cards, these would qualify for lifetime platinum status. The instrument's sensitivity is so extreme that it can detect the heat signature of a bumblebee at the distance of the moon, at least in theory, which is comforting because if cosmic anomalies don't pan out, there's always lunar beekeeping. Yet the data persists. Multiple observations, independent analyses, different teams. The object remains stubbornly luminous and uncomfortably mature for its assigned epoch. You can feel the mood shift in the virtual meeting rooms where astronomers gather. Excitement mixed with restraint. No one wants to overstate the case. Scientific reputations are built on careful language, suggests, indicates, consistent with. Rarely this breaks reality, but privately the whispers grow louder. If Webb is correct, and so far it has performed spectacularly well, then either galaxy formation began earlier and proceeded faster than expected, or the underlying cosmological parameters need tweaking. You glance again toward that imagined golden mirror, floating in its cold, silent orbit. It doesn't care about theoretical discomfort. It simply collects light. And that light, ancient and stretched thin, continues to paint a picture that refuses to match the one you've been carrying in your mind. A tidy timeline from hot plasma to first stars to gradual cosmic architecture. The telescope has done its job. It has looked where we asked it to look. The unsettling part is that it found exactly what it saw. And as the data deepens, you realize this isn't just about one bright speck in the dark. It's about whether the early universe grew up far too quickly or whether your cosmic calendar has been missing a few pages. You let the telescope drift into the background of your thoughts and focus instead on the light itself. Those faint, elongated waves that have been stretching across space since the universe was barely out of its infancy. The numbers on the screen glow softly. Redshift values so high they nudge against the edges of expectation. Redshift is beautifully simple in principle. As space expands, it stretches the wavelength of traveling light. The greater the stretch, the farther away, and the further back in time you're looking. Edwin Hubble formalized this in 1929, showing that distant galaxies recede faster the farther away they are. The universe, once assumed static, was expanding. It was one of the most transformative discoveries in modern science. But here's where your eyebrows start to lift. The redshift of this object places it roughly 300 to 400 million years after the Big Bang. That's during what cosmologists call the cosmic dawn, when the very first stars were igniting and the fog of neutral hydrogen was slowly being burned away by ultraviolet radiation. The universe was still dim, patchy, and chaotic, at least according to prevailing models. Yet the spectral data suggests a complexity that feels premature. You zoom in on absorption lines, specific wavelengths where elements absorb light. These lines act like chemical fingerprints. Hydrogen and helium are expected this early. They were forged in the first few minutes after the Big Bang during primordial nucleosynthesis. Heavier elements, carbon, oxygen, iron, require stars, big ones, exploding ones. And that's the issue. The light from this object hints at metals. Astronomers charmingly refer to any element heavier than helium as a metal, which makes oxygen sound like it belongs in a hardware store. The presence of these heavier elements implies that at least one full generation of stars has already lived and died. That takes time. Mainstream cosmology suggests the first stars formed perhaps 100 to 200 million years after the Big Bang. They were likely massive, hundreds of times the mass of our sun, and burned hot and fast, ending their lives in spectacular supernovae. Those explosions seeded space with heavier elements, allowing subsequent generations of stars and galaxies to become chemically richer. But fitting multiple stellar generations into just a few 100 million years is ambitious. It's like expecting a forest to mature, burn down, and regrow before your weekend camping trip ends. Historians still argue whether the early universe's structure formation was a smooth, gradual process or punctuated by rapid bursts of intense activity. The simulations tend to favor gradual clustering under the influence of dark matter halos. Matter falls in, stars ignite, feedback from supernovae regulates further growth, a cosmic balancing act. Yet this object looks like it skipped the rehearsal and went straight to opening night. There's also the matter of brightness. Luminosity correlates with stellar mass. The more stars you have, especially massive young ones, the brighter your galaxy shines in ultraviolet and infrared. This object isn't shy. It beams confidently across billions of light years. Could the redshift be misinterpreted? That's the first line of defense. Photometric redshifts estimated from brightness across different filters can sometimes mislead. Dust within galaxies can mimic the color signatures of extreme distance. But follow-up spectroscopy tightens the constraints. Spectral lines shift in precise, measurable ways. In this case, the data seems stubborn. You imagine ancient photons stretching like taffy as the universe expands. A photon emitted in ultraviolet 13.4 billion years ago arrives at Webb's detectors as infrared. It has endured the entire history of cosmic expansion. Continents formed, dinosaurs rose and fell, mammals evolved, humans invented sourdough starters, and that photon just kept going. And now it tells you something awkward. There's a quirky historical parallel here. In the early 20th century, astronomers debated the age of the universe based on measurements of the Hubble constant, the rate of expansion. Early estimates suggested an age younger than Earth itself, which was problematic. Imagine realizing the planet you're standing on appears older than the cosmos it supposedly formed in. That discrepancy eventually resolved with better measurements and refined physics. You can't help wondering if you're watching a similar tension unfold. If the object truly formed when the redshift suggests, then galaxy assembly must have been astonishingly efficient. Gas would have had to cool, collapse, and form stars at breakneck speed. Dark matter halos would need to gather mass quickly enough to anchor these structures gravitationally. And here's where the room gets quiet, the redshift might not mean exactly what you think it means. Redshift is typically interpreted as purely cosmological, caused by the expansion of space itself. But there are other contributions to redshift. Gravitational redshift, where light loses energy escaping a massive object's gravitational field, and Doppler shifts from peculiar velocities. Normally, these effects are minor compared to cosmic expansion at such distances. Normally, you stare at the graph. The curve fits beautifully within error bars, statistically robust. No obvious anomalies in the data reduction pipeline. The software has been vetted. Calibration checks pass. So the light appears older than it should be, not in the sense that it's physically impossible, but in the sense that the structure emitting it seems too developed for that era. It's like carbon dating a smartphone to the Roman Empire. Either your dating method is flawed, or Caesar had surprisingly good Wi-Fi. Astronomers begin drafting cautious papers. Words like unexpected, surprisingly luminous, and challenging to reconcile appear. No one writes physics is broken, not yet. Because the Big Bang model itself is supported by multiple independent pillars: cosmic microwave background radiation, abundance of light elements, large-scale structure distribution. It's not a flimsy theory propped up by one telescope. It's a deeply interwoven framework. But frameworks can flex. The more you sit with the data, the more the timeline feels compressed. Cosmic dawn seems less like a gentle sunrise and more like someone flipping on stadium lights. And the uncomfortable possibility begins to settle in. Perhaps the early universe wasn't as slow and simple as the textbooks imply. Perhaps structure emerged faster, or perhaps some ingredient, dark matter behavior, initial density fluctuations, something subtle, needs revisiting. You imagine the universe at 300 million years old, still hot in places, still ionizing hydrogen, and already, apparently, building grand structures with an efficiency that borders on audacious. The light continues to stream in, indifferent to your theoretical discomfort. Ancient, stretched, unapologetic. And if its timestamp is correct, then the next question becomes even more unsettling. Not just how old it is, but how something so mature managed to exist at all. You let the age question hover for a moment and instead focus on shape, because it's one thing for a galaxy to exist early. It's another for it to look organized. On your screen, brightness contours form something more structured than expected. Not a chaotic puff of star-forming knots, but a concentrated, almost symmetrical body. There are hints, subtle, but there of a central bulge. Density gradients, possible disk-like features. For an object that supposedly formed when the universe was still in its cosmic toddler phase, it looks suspiciously grown up. In the standard model of galaxy formation, small clumps of matter merge over time. Tiny proto-galaxies collide and combine, building larger structures through hierarchical assembly. It's cosmic Lego, but very slow Lego. You don't get a grand spiral overnight. You get lumps that gradually settle into more stable configurations over billions of years. The Milky Way itself is thought to have grown through repeated mergers. Evidence of this still lingers in stellar streams, long ribbons of stars that are remnants of smaller galaxies torn apart by gravity. In fact, in 2018, astronomers identified evidence of an ancient merger event called Gaia Enceladus, which significantly shaped the Milky Way's structure. Our galaxy is basically a scrapbook of past collisions. So when you look at this distant object, barely a few 100 million years after the Big Bang, and it appears compact and well-formed, something feels off. It's too tidy. Early galaxies, according to simulations, should be turbulent. Gas clouds collapsing rapidly, supernovae detonating frequently, radiation blasting through surrounding material. It should look messy, irregular, almost unfinished. Instead, this one seems to have settled down early, like a child who skipped the chaotic toddler phase and went straight to filing taxes. The brightness profile suggests a dense stellar population. That implies efficient star formation. And efficient star formation requires cool gas that has had time to lose energy, condense, and fragment into stars. But cooling mechanisms in the early universe were limited. Without abundant heavy elements, gas doesn't radiate heat as effectively. Metal-poor gas is stubbornly warm. And yet here you are, staring at what appears to be a galaxy that cooled, condensed, and structured itself with impressive speed. Historians still argue whether early galaxy formation was dominated by rapid, monolithic collapse, large clouds forming stars in a single dramatic burst, or by gradual hierarchical merging. Most modern evidence favors the latter, but this object nudges the debate back toward the former, at least for some cases. You scroll through simulated comparisons. The computer models based on dark matter halo growth rates and baryonic physics predict certain mass distributions at this epoch. This galaxy seems to overshoot them. Could it be an observational illusion? Gravitational lensing remains a suspect. Massive foreground objects can magnify and distort background galaxies, making them appear brighter and sometimes more structured than they truly are. Einstein's general relativity predicts that mass curves space-time, bending the path of light. Entire galaxy clusters can act as cosmic magnifying glasses. The Hubble Space Telescope has captured spectacular examples of this. Luminous arcs and multiple images of the same background galaxy warped around a foreground cluster. If this object were lensed, its brightness could be artificially boosted. But detailed analysis shows no obvious foreground cluster aligned perfectly to create such a dramatic magnification. No telltale arcs, no duplicated images. It appears standalone. There's also a quirky, lesser-known historical note. In the 1940s, astronomer Walter Baade reclassified stellar populations and effectively doubled the estimated size of the universe at the time by refining distance measurements. A single recalibration shifted humanity's cosmic scale. It's a reminder that sometimes the universe isn't wrong, our yardstick is. So maybe this is another yardstick problem. Still, the structural maturity keeps tugging at you. Galactic morphology usually evolves over time. Spirals, ellipticals, irregulars. These categories describe shapes influenced by mergers, star formation rates, and angular momentum. Mature galaxies often show defined components: bulges, disks, halos. If this early object truly possesses a dense central region suggestive of a bulge, then it implies rapid mass concentration. That in turn suggests significant gravitational potential early on. Dark matter halos are thought to provide the scaffolding for such formation. In the Lambda-CDM model, tiny density fluctuations in the early universe, visible today as slight temperature variations in the cosmic microwave background, grew over time under gravity. Those fluctuations seeded structure. The Planck satellite, which mapped the cosmic microwave background with exquisite precision, confirmed these tiny anisotropies. They're on the order of 1 part in 100,000. From those minute ripples, all galaxies eventually formed. But perhaps some ripples were taller than expected. There's ongoing scholarly debate about whether small-scale structure formation might be more efficient than current simulations suggest. Feedback processes, stellar winds, radiation pressure, supernova explosions are notoriously complex to model. Tiny changes in assumptions can lead to significant differences in predicted galaxy growth rates. You imagine the early universe not as a gentle simmer, but as a rapid boil, pockets of intense activity where matter clumped aggressively. Still, the maturity implied here strains comfort. It's like opening a time capsule labeled Ancient Beginnings and finding a polished metropolis inside. And here's a slightly fringe thought that's been whispered in corners of conferences. What if certain regions of the early universe experienced accelerated structure formation due to variations in dark matter properties? Warm dark matter, self-interacting dark matter, alternative models tweak how quickly halos form and merge. These ideas remain speculative, but anomalies like this give them oxygen. You sit with the image again, the faint glow, the structured brightness, the implication of density and order emerging faster than expected. The universe was supposed to take its time. Gravity, after all, is patient. It gathers dust slowly, it builds stars gradually, it crafts galaxies over eons. And yet this one appears to have skipped the line. The unsettling part isn't just that it exists early, it's that it looks like it's been there a while. And if galaxies could mature this quickly, then the cosmic timeline might not just be compressed, it might be fundamentally misunderstood. You exhale softly in the dim control room glow. Because if structure formed this fast, then something at the heart of cosmic evolution may be more efficient, more dynamic, and more unpredictable than you've allowed yourself to believe. And at the center of that structure, there's another detail waiting to complicate things even further. You narrow your focus toward the heart of the galaxy, the luminous core where gravity pulls hardest and light burns brightest. Because if the outer structure is unsettling, the center is downright audacious. At the core of most large galaxies today sits a supermassive black hole. The Milky Way hosts one called Sagittarius A, weighing in at about 4 million times the mass of our Sun. In 2022, astronomers released the first image of it, a fuzzy orange ring surrounding a dark shadow captured by the Event Horizon Telescope. It was a triumph of global collaboration in radio interferometry, a reminder that even invisible things can leave signatures. But Sagittarius A is modest compared to some cosmic heavyweights. In 2019, the Event Horizon Telescope also imaged the black hole in galaxy M87, which has a mass of about 6.5 billion suns. That's not a typo. Billion. These monsters anchor galaxies and influence star formation through energetic jets and radiation. Here's the catch. Supermassive black holes take time to grow. They likely begin as seed black holes, either remnants of massive early stars collapsing under their own gravity or formed via direct collapse of enormous gas clouds. From there, they grow by accreting matter and merging with other black holes during galactic collisions. But even under optimistic growth rates, accreting at what's called the Eddington limit, there's a speed cap. Radiation pressure from infalling material pushes outward, limiting how fast mass can accumulate, which brings you back to this early galaxy. The luminosity of its core suggests the possible presence of an actively feeding black hole, a quasar-like engine pouring out radiation. If confirmed, the implied mass would be enormous for such a young universe, potentially hundreds of millions of solar masses. And now you have a scheduling crisis, because building a black hole that massive in just a few 100 million years strains conventional growth models. Even if you start with a hefty seed, say 100 solar masses from a population 3 star, you'd need near-continuous rapid accretion to reach those sizes so quickly. No breaks, no cosmic coffee pauses. Historians still argue whether the earliest supermassive black holes formed from stellar remnants that grew steadily or from direct collapse scenarios where massive gas clouds bypassed star formation and collapsed straight into black holes of 10,000 to 100,000 solar masses. The latter would provide a head start, but even then, the timeline feels tight. And this isn't the first time astronomers have faced this puzzle. Even before Webb, Distant quasars had been discovered at redshifts corresponding to less than a billion years after the Big Bang. In 2001, a quasar designated SDSS-J10300524 was found at a redshift of 6.28, already hosting a black hole about 2 billion solar masses. That discovery raised eyebrows. Webb is now pushing those boundaries even earlier. You lean closer to the data. The spectral signatures hint at energetic processes, ionized gas, high-energy emissions. Not definitive proof of a black hole, but strongly suggestive. There's also a quirky historical parallel here. In the 18th century, English natural philosopher John Michell proposed the idea of dark stars whose gravity would be so strong that even light couldn't escape. This was long before Einstein's relativity formalized the concept of black holes. Michell's idea was largely forgotten for centuries. Sometimes science plants seeds that don't sprout until much later. Now, centuries on, you're grappling with black holes that may have grown too big, too fast. One possibility is super Eddington accretion, brief periods where black holes grow faster than traditionally assumed. Under certain conditions, radiation may escape in ways that allow more matter to fall in than the classic limit suggests. It's messy physics, involving thick accretion disks and anisotropic radiation flows, but it's being actively studied. Another possibility is that early universe conditions were unusually favorable. Gas densities were higher, mergers were more frequent. Maybe black holes simply had more to snack on. Still, the implied mass remains uncomfortable. Because if such massive black holes were common this early, they would influence their host galaxies profoundly. Intense radiation and outflows could regulate star formation, heating and expelling gas. The interplay between black hole growth and galaxy evolution, called coevolution, is one of the central themes in modern astrophysics. Yet here, coevolution appears to be sprinting. You imagine the early universe as a crowded nursery of galaxies, each trying to grow, merge, and ignite stars, while in their centers, gravitational wells deepen rapidly, swallowing matter and blazing as quasars. There's even a fringe hypothesis occasionally whispered at conferences: primordial black holes. These hypothetical objects could have formed from density fluctuations in the very early universe, moments after the Big Bang, long before stars existed. If some of these were sufficiently massive, they could serve as oversized seeds for early supermassive black holes. The idea remains speculative, and observational evidence is inconclusive, but anomalies like this give such theories renewed attention. Of course, caution remains paramount. The data must be confirmed, mass estimates refined, alternative explanations ruled out. But you can't ignore the tension. A galaxy that looks mature, light that appears older than its structural development should allow. And at its center, possibly, a gravitational titan that had no business growing so large so quickly. It's as if the universe didn't just light its first candles, it built entire bonfires. You sit back and consider the implications. Black holes are not exotic outliers. They are integral to cosmic architecture. If their formation timeline shifts, so too does the story of galaxy formation, star regulation, and large-scale structure. And if this black hole truly exists at the mass implied, then the early universe was not just industrious. It was astonishingly efficient. Efficient in a way that nudges at the edges of your theoretical comfort zone. Because somewhere in those first few 100 million years, gravity may have been working overtime. And the deeper you peer into that luminous core, the more it feels like the cosmos is daring you to reconsider how quickly the impossible can happen. You return to the numbers, because numbers are supposed to calm you down. They're tidy, predictable, comforting in a way that luminous cosmic rule breakers are not. At the center of this puzzle sits a single value: redshift. Redshift doesn't just tell you distance, it tells you about the expansion of the universe itself. The higher the redshift, the more space has stretched since the light began its journey, and that stretching is governed by the Hubble constant, the rate at which the universe expands today. Here's where things get spicy in the most academically polite way possible. For years now, cosmology has been dealing with what's called the Hubble tension, measurements of the expansion rate based on observations of the early universe, particularly from the cosmic microwave. Background mapped by the Planck satellite suggests a value of about 67 kilometers per second per megaparsec. Meanwhile, measurements based on nearby supernovae and Cepheid variable stars indicate a faster expansion rate, closer to 73 kilometers per second per megaparsec. That might not sound like much of a difference. 6 kilometers per second? You could jog that. But in cosmology, that gap is enormous. It implies something in our understanding is slightly off, either about early universe physics or about how expansion behaves over time. And now this galaxy strolls in, flashing a redshift that fits within current frameworks, yet seems to produce consequences that don't. If the expansion rate were different in the early universe, even subtly, timelines would shift. Structures could form earlier or later than predicted. Small deviations compound over billions of years. Historians still argue whether the Hubble tension represents unknown systematic errors in measurement or hints at new physics beyond the standard Lambda-CDM model. Some propose modifications to dark energy behavior. Others suggest additional relativistic particles in the early universe, sometimes dubbed early dark energy. You stare at the redshift value again. It's not just high, it's precise. Spectroscopic confirmation reduces the uncertainty. The absorption lines are shifted consistently. The signal-to-noise ratio is solid. The data pipeline has been vetted by multiple independent teams. So if the redshift is correct, the timing is correct. And if the timing is correct, then either galaxy formation models are incomplete or something about cosmic expansion needs adjusting. There's also the subtle question of how redshift is interpreted. In standard cosmology, redshift is due to the expansion of space itself. Light waves stretch as the fabric of space-time expands. This isn't objects flying through space away from us in the conventional sense. It's space itself expanding between objects. That idea stems from Einstein's general relativity, published in 1915. Einstein initially resisted the notion of an expanding universe and even introduced a cosmological constant to keep the universe static. He later reportedly referred to that as his greatest blunder after Hubble's discovery of expansion. Ironically, the cosmological constant, now associated with dark energy, is back in the equations. Cosmology has a sense of humor. You imagine space itself as a vast elastic sheet slowly stretching, carrying galaxies along for the ride. The farther the light travels, the more it stretches. That's redshift. But what if something subtle is happening along the way? Some alternative models well outside mainstream consensus have proposed non-expansion explanations for redshift, such as tired light hypotheses, where photons lose energy over distance. These ideas have largely been ruled out because they fail to explain other observations, like the time dilation seen in distant supernova light curves. Still, when anomalies appear, even old discarded ideas get dusted off for a second look. Not because they're likely correct, but because science checks. Back in the control room, you notice the way discussions are shifting. No one is claiming expansion is wrong. That would require dismantling an enormous body of evidence. Instead, the question becomes more refined. Could early cosmic conditions have allowed for faster than expected structure formation without altering the overall expansion model? Perhaps density fluctuations were slightly more pronounced at small scales. Perhaps dark matter clumped more efficiently. But the redshift problem isn't just about timing. It's about consistency. The brightness and inferred mass of this object don't neatly align with the expected abundance of such massive systems at that epoch. In statistical terms, it might be a rare outlier, and the universe does produce outliers. In 2003, astronomers discovered a star, He 0107-5240, with an extremely low metal content, one of the most primitive stars ever observed. It defied expectations about early star formation and forced refinements in models. Rare doesn't mean impossible. Yet the concern here is frequency. If Webb begins finding not just one, but several such early massive galaxies, then rarity becomes pattern. You scroll through preliminary survey data, a handful of candidates. Some slightly less extreme, but still uncomfortably bright. You can feel the gentle pressure building, not explosive, not dramatic, just persistent. The redshift values are like timestamps carved in cosmic stone. They insist these objects belong to an era when the universe was supposed to be in its architectural infancy. And yet their properties suggest adolescence, if not early adulthood. There's a quiet debate simmering. Are we underestimating the efficiency of gas cooling and star formation in primordial halos? Or are our assumptions about dark matter behavior incomplete? Self-interacting dark matter models, for example, alter how quickly halos concentrate mass. It's subtle, technical, the kind of debate that happens over conference coffee, accompanied by scribbled equations and raised eyebrows. You lean back and imagine stretching a timeline across the wall. The Big Bang at one end, today at the other. Somewhere very near the beginning, you now have a galaxy that looks like it jumped ahead several chapters. The redshift says it belongs there. The structure says it doesn't. And until those two statements reconcile, you're left with a gently throbbing question in the back of your mind. Is the universe expanding exactly the way you think it is? Or has it been keeping a small, mathematically elegant secret all along? You let the expansion debate simmer and shift your attention to something you cannot see at all: dark matter. Roughly 27% of the universe is thought to be made of this invisible substance. Not atoms, not light, not anything in the standard model of particle physics. You can't photograph it, you can't scoop it into a jar, but you can watch what it does. Galaxies rotate too fast for their visible matter alone to hold them together. In the 1970s, astronomer Vera Rubin meticulously measured the rotation curves of spiral galaxies and found that stars far from the galactic center were orbiting just as quickly as those closer in. According to Newtonian gravity, they should have been flung outward. Something unseen was providing extra mass, extra gravity. Rubin's work became one of the strongest pieces of evidence for dark matter. So in your cosmic blueprint, dark matter acts like scaffolding. It collapses first into halos, creating gravitational wells into which ordinary matter, gas, dust, stars, falls. Without dark matter, galaxies as we know them would not form, which makes this early, overachieving galaxy particularly interesting. If it grew so massive so quickly, perhaps its dark matter halo assembled at an accelerated pace. Maybe the scaffolding went up faster than expected. In the standard Lambda-CDM model, dark matter is cold, meaning its particles move relatively slowly compared to the speed of light. Slow-moving particles clump efficiently, allowing small structures to form first, then merge into larger ones. Simulations using cold dark matter reproduce large-scale cosmic structure remarkably well. The web-like pattern of galaxy clusters and filaments stretching across the universe. But small-scale behavior remains an area of active research. Historians still argue whether discrepancies in small galaxy distributions, the so-called missing satellites problem, indicate flaws in simulations or deeper issues with the cold dark matter assumption. Some propose warm dark matter composed of lighter, faster-moving particles that smooth out small-scale clumping. Others suggest self-interacting dark matter, where particles occasionally bump into each other, altering halo density profiles. Now imagine this. What if, in the early universe, dark matter behaves slightly differently than expected? Not dramatically, just enough to enhance early halo concentration. A denser halo would deepen the gravitational well, pulling gas inward more efficiently. Faster gas collapse, faster star formation, faster growth. Suddenly, that prematurely mature galaxy doesn't look quite as impossible, just reinterpret it. You pull up gravitational lensing data again. Even when not producing dramatic arcs, dark matter leaves subtle signatures by bending background light. By mapping these distortions statistically across the sky, astronomers infer the distribution of dark matter. The fact that gravitational lensing works so consistently across cosmic scales strongly supports its existence, and yet its true nature remains elusive. There's even a quirky twist in the story. In the early 2000s, experiments searching for dark matter particles deep underground, shielded from cosmic rays, began reporting occasional unexplained signals. None have been definitively confirmed as dark matter interactions. It's as if the universe is playing hide-and-seek with the most abundant matter we can't see. Back in your imagined control room, the anomaly's mass estimates depend partly on assumptions about dark matter halo structure. If the halo is unusually concentrated, it could explain the galaxy's rapid assembly. But there's a tension here too, because if dark matter halos form faster than predicted, that would ripple through many areas of cosmology. It would alter predictions about galaxy clustering, merger rates, and even the timeline of reionization, the epoch when the first stars and galaxies ionized neutral hydrogen in the intergalactic medium. The cosmic microwave background gives us constraints on how matter behaved early on. Tiny fluctuations in temperature mapped exquisitely by the Planck satellite encode information about dark matter density and behavior shortly after the Big Bang. Those maps fit beautifully with cold dark matter assumptions. So if dark matter is misbehaving here, it's doing so in a way subtle enough to evade earlier detection. You imagine the early universe as a vast dark ocean. Ordinary matter floats like luminous foam on top, visible and familiar. Beneath it, unseen currents, dark matter, shape the movement of everything. What if in certain regions those currents were stronger? There's also the controversial idea of modified gravity theories, such as modified Newtonian dynamics, which attempt to explain galactic rotation curves without invoking dark matter. These theories have had mixed success and struggle to explain observations on large cosmological scales. Still, anomalies tend to revive old debates. You don't jump to modified gravity. That would be like remodeling the entire house because one window sticks. But you can't ignore the possibility that the invisible scaffolding of the universe might be slightly different than assumed. If this galaxy's halo assembled unusually quickly, perhaps due to rare high-density fluctuations, it might simply represent an extreme statistical outlier. The universe spans billions of light years. Given enough volume, rare events become inevitable. And yet, as more candidates appear in Webb's deep fields, the outlier argument grows thinner. You feel the weight of invisible mass pressing into the equations. Dark matter has always been the quiet partner in cosmic evolution, never seen, always inferred. Now with this object, it feels like that partner might be improvising, not abandoning the dance, just adding a few unexpected steps. And as you trace the gravitational contours implied by this impossible galaxy, you begin to wonder whether the universe's hidden framework is sturdier, denser, or more dynamic than you've given it credit for, because if the scaffolding went up early and fast, then everything built upon it could rise just as quickly. You take a slow breath and turn inevitably toward Einstein. Because whenever gravity behaves in surprising ways, his shadow stretches across the conversation. General Relativity, published in 1915, describes gravity not as a force, but as the curvature of space-time caused by mass and energy. Planets orbit stars because they follow curved paths in warped space-time. Light bends around massive objects because space-time itself is curved. The equations are elegant, nonlinear, and famously difficult to solve without strong coffee. And so far, they've been astonishingly successful. General Relativity predicted gravitational lensing, gravitational time dilation, and even gravitational waves, ripples in space-time produced by massive accelerating objects. In 2015, a century after Einstein's prediction, LIGO detected gravitational waves from merging black holes. The signal lasted fractions of a second, but it confirmed yet another piece of his framework. If Einstein had a cosmic scorecard, it would be embarrassingly impressive. So no one is casually suggesting relativity is wrong. But cosmology operates on the largest possible scales. And on those scales, relativity blends with assumptions about dark matter, dark energy, and the uniformity of space-time. If something in the early universe formed faster than expected, it's fair, quietly, respectfully, to ask whether gravity behaved exactly as assumed under those conditions. Historians still argue whether Einstein himself would have embraced modifications to his equations if compelling anomalies emerged. He famously introduced the cosmological constant to maintain a static universe, then reconsidered it. Science, even at its most brilliant, adapts. In the case of this impossible galaxy, gravity plays a central role. Structure formation depends on how quickly matter collapses under its own weight. If gravity were slightly stronger on certain scales in the early universe, overdense regions could have grown more rapidly. There are theoretical frameworks that explore such possibilities. Some modified gravity models, like scalar tensor theories, introduce additional fields that subtly alter gravitational behavior over cosmic time. Others consider the possibility that gravity's strength evolves. These ideas remain speculative and tightly constrained by observation. Solar system tests, binary pulsar timing, and gravitational wave signals all confirm general relativity with high precision. You can't just tweak gravity without consequences. Still, when faced with an object that appears to defy growth timelines, researchers explore parameter space carefully. You picture space-time itself in those early epochs, dense, hot, rapidly expanding. The cosmic microwave background tells us the universe was remarkably uniform, but not perfectly so. Tiny fluctuations, quantum in origin, magnified during inflation, seeded everything that followed. Inflation itself is another fascinating chapter. Proposed in the early 1980s by Alan Guth and others, it suggests that the universe underwent a brief period of exponential expansion, fractions of a second after the Big Bang. This would explain the large-scale uniformity of the cosmos and the absence of exotic relics predicted by earlier models. Inflation has strong indirect support, but its precise mechanism remains uncertain. And here's the intriguing part. Inflation set the initial conditions, the distribution of density fluctuations, the seeds. If those seeds were slightly different, if certain regions experienced slightly enhanced fluctuations, gravity could amplify them rapidly. You glance again at the galaxy's inferred mass. Its gravitational potential well must be deep. Gas must have fallen inward efficiently. Stars must have ignited in large numbers. Could gravity have been more efficient in funneling matter during that epoch? There's also the possibility of early dark energy, an additional energy component that briefly altered expansion dynamics before fading away. Some models propose that a temporary boost in expansion or gravitational behavior could ease tensions like the Hubble discrepancy. These models are mathematically intricate and tightly constrained, but they're being actively explored. You imagine Einstein sitting quietly in the corner of the control room, hair slightly untamed, listening to the data presentation. He doesn't object, he doesn't defend, he simply waits for the math. Because in the end, relativity is math. And math either holds or it doesn't. There's a quirky anecdote from 1919 when Einstein was asked what he would think if the eclipse observations hadn't confirmed his prediction about light bending. He reportedly replied, "Then I would have been sorry for the dear Lord because the theory is correct. Confidence level, cosmic." But even Einstein knew that no theory is beyond revision if evidence demands it. At present, there's no direct evidence that general relativity fails here. The equations still describe black holes, gravitational lensing, and cosmic expansion beautifully. Yet this early galaxy presses against the edges of expectation. If gravity and dark matter work together just a bit more efficiently than modeled, perhaps the anomaly dissolves into statistical rarity. But if more such galaxies appear, if the pattern strengthens, then cosmologists may need to revisit assumptions about how space-time, matter, and energy interacted in those first few 100 million years. You look once more at the data. The redshift, the luminosity, the implied mass. Nothing overtly violates Einstein's equations, and yet the outcome feels accelerated, like gravity briefly had its foot pressed harder on the pedal. You let that image settle, space-time curving, matter flowing, light bending obediently along geodesics, all exactly as relativity prescribes. And still, somehow, structures rising faster than predicted. It's not a rebellion against Einstein. Not yet. But it is a quiet reminder that even the most successful theories can be nudged by new observations. And as you continue tracing the consequences of this impossible object, you begin to sense that the tension isn't loud or dramatic. It's subtle, a slight strain in the cosmic fabric. Just enough to make you wonder whether space-time itself might have a few more surprises folded into its elegant curves. You let gravity rest for a moment and drift even further back, past the first stars, past the first atoms, back to a time when the universe was a glowing, opaque plasma. Because if something seems off in the early timeline, you have to consult the oldest light of all. About 380,000 years after the Big Bang, the universe cooled enough for protons and electrons to combine into neutral hydrogen. Before that, photons scattered constantly off free electrons, trapped in a dense fog. But once neutral atoms formed, light could finally travel freely. That ancient light still fills the cosmos today as the cosmic microwave background, faint, nearly uniform radiation detectable in every direction. It was discovered accidentally in 1965 by Arno Penzias and Robert Wilson, who were troubleshooting persistent noise in a radio antenna. They even cleaned out pigeon droppings, thinking that might be the culprit. It wasn't. The noise was the afterglow of creation itself. Imagine sweeping up cosmic history with a broom. Since then, missions like COBE, WMAP, and Planck have mapped this background radiation in exquisite detail. Tiny temperature fluctuations, about 1 part in 100,000, encode information about the universe's composition, age, and geometry. From those ripples, cosmologists derive parameters that underpin the Lambda-CDM model. Those ripples are the seeds of all structure. Regions slightly denser than average eventually collapsed under gravity to form galaxies and clusters. Regions slightly less dense became vast cosmic voids. The large-scale structure of the universe today, filaments, clusters, and walls, can be traced back mathematically to those minute variations in the microwave background. And here's the tension. The cosmic microwave background suggests a specific distribution of initial density fluctuations. Those distributions, when fed into simulations, produce predictions about how many massive galaxies should exist at various epochs. This galaxy appears to overshoot those predictions. Historians still argue whether our interpretation of the microwave background's fine structure leaves room for small-scale anomalies that might accelerate early structure formation. The data fits remarkably well, but remarkably well doesn't mean perfectly. You picture the early universe as a softly glowing sphere modeled with barely perceptible temperature differences. Quantum fluctuations during inflation were stretched to cosmic scales, imprinting that pattern. Those fluctuations are random but statistically constrained. If this early, mature galaxy formed from an unusually high-density peak, one of the rare tallest ripples, it might simply represent the extreme tail of the distribution. Statistical outliers happen. If you flip a coin enough times, eventually you'll get a surprising streak. The universe has had 13.8 billion years and trillions of galaxies to play with. But there's another layer. The cosmic microwave background also constrains the overall matter density and dark matter fraction. Those values feed directly into growth rate calculations. If early structure formed faster than expected, perhaps the growth rate of density perturbations differs slightly from predictions. There's a concept called sigma-8, which measures the amplitude of matter fluctuations on certain scales. Tensions between sigma-8 values derived from cosmic microwave background measurements, and those inferred from large-scale structure surveys have been discussed for years. They're subtle discrepancies, but subtle is how revolutions begin. You stare at the Planck parameter tables. They're precise to several decimal places. The age of the universe, 13.8 billion years. The baryon density, the dark matter fraction. The curvature parameter, consistent with a flat universe within tiny margins. Flat, uniform, predictable, and yet this galaxy rises too quickly from that calm statistical sea. There's even a fringe, though intriguing. Line of speculation. What if inflation produced slightly non-Gaussian fluctuations, departures from the simple statistical distribution usually assumed? That could allow for more extreme early overdensities. Current observations constrain non-Gaussianity tightly, but the door isn't mathematically slammed shut. You imagine one tiny region in that early plasma being just a bit denser than average. Just enough that over millions of years, gravity amplifies it dramatically, like a slightly taller wave in an ocean that eventually becomes a towering crest. Could that be what you're seeing? Or does the existence of multiple such early massive galaxies imply that the initial conditions were more favorable to rapid growth than believed? The microwave background is often described as the universe's baby picture, smooth, softly glowing, innocent-looking, but baby pictures don't tell you everything about the adult. The light from this impossible galaxy suggests that, somewhere in that infant snapshot, there were seeds capable of astonishing acceleration. You feel the weight of deep time pressing gently against your thoughts. From 380,000 years after the Big Bang to 300 million years later, a blink in cosmic terms, something assembled a complex, massive structure that now challenges your expectations. It doesn't contradict the microwave background outright, but it leans against it. And if future observations confirm that such galaxies were not vanishingly rare, cosmologists may need to revisit how those primordial ripples evolved into the grand cosmic web. For now, the background radiation remains your most reliable narrator of early history, but even narrators can leave out details. And somewhere between that ancient microwave whisper and this unexpectedly mature galaxy, there may be a missing line in the story, subtle, mathematical, but profound. You sit quietly with that thought, suspended between the oldest light in existence and a galaxy that seems to have grown up too fast. The universe began in simplicity. At least that's what you were told. But simplicity, as it turns out, can hide extraordinary potential. You zoom in not on the galaxy as a whole this time, not on its dark matter halo or its potentially overachieving black hole, but on the tiny, restless world of particles. Because sometimes the biggest cosmic puzzles begin at the smallest scales. Every star in that distant galaxy is powered by nuclear fusion, hydrogen nuclei fusing into helium under immense pressure and temperature. That much is familiar. But the conditions under which the first stars formed were very different from those in later generations. The early universe had almost no heavy elements. Cooling mechanisms were limited. Gas clouds had to rely primarily on molecular hydrogen to shed heat and collapse. That's why the first stars, population 3 stars, are thought to have been enormous. Without metals to help gas fragment into smaller clumps, the collapsing clouds likely formed stars hundreds of times the sun's mass. These stars would have burned hot and fast, living only a few million years before exploding as supernovae. Mainstream astrophysics holds that these early giants seeded the cosmos with the first heavy elements, enabling subsequent generations of smaller, longer-lived stars. So here's the microscopic tension. If this galaxy appears chemically enriched very early, then star formation and therefore nuclear processes must have ramped up with astonishing speed. You picture hydrogen atoms drifting in the early dark, cooling just enough to clump. Quantum mechanics governs every step of that process. Electrons shifting energy levels, molecules forming, photons emitted as gas cools. On the smallest scales, the rules are exquisitely precise, and yet the large-scale outcome seems unexpectedly accelerated. Historians still argue whether our models of early star formation adequately capture the complexity of gas dynamics and feedback at quantum and atomic levels. Simulations necessarily simplify. They approximate cooling rates, turbulence, magnetic fields, but in reality, interstellar gas behaves like a chaotic orchestra of particles, fields, and radiation. A slight change in cooling efficiency, just a few percent, could dramatically alter collapse timescales. There's also the role of radiation feedback. Massive stars emit intense ultraviolet light that ionizes surrounding hydrogen, heating it and potentially suppressing further star formation nearby. It's a self-regulating mechanism. Too many stars too quickly, and the environment pushes back. But what if, in certain early regions, that feedback loop was less effective? Perhaps gas densities were high enough to shield collapsing regions from radiation. Perhaps turbulence redistributed energy differently than models predict. Then there's the chemistry. Even trace amounts of heavy elements, carbon, oxygen, can significantly enhance cooling by allowing gas to radiate energy more efficiently. If enrichment occurred extremely rapidly after the first supernovae, second-generation stars might have formed sooner and in greater numbers than expected. You think about the first supernovae detonating in the dark? Those explosions would have been titanic, briefly outshining entire galaxies. The shock waves would propagate through surrounding gas, compressing some regions while dispersing others. It's not purely destructive. Supernovae can also trigger new star formation by compressing nearby clouds. The interplay is delicate, violent yet creative. And at the heart of it all, quantum mechanics quietly dictates the probabilities of nuclear reactions and atomic transitions. Here's a quirky twist. The precise energy levels of carbon atoms, the so-called Hoyle state, are finely tuned in a way that allows carbon to form efficiently inside stars. Without that resonance, life as we know it wouldn't exist. Fred Hoyle predicted this energy state before it was experimentally confirmed, reasoning that carbon must be producible in stars in sufficient quantities. Sometimes theoretical necessity leads to real discovery. So when you consider this early galaxy's apparent chemical maturity, you're really considering billions upon billions of atomic interactions unfolding faster than expected. It's not that quantum mechanics is broken. It's that the emergent behavior, the large-scale outcome of countless tiny interactions, might be more efficient under primordial conditions than your models assumed. You imagine the early universe not as sparse and hesitant, but as energetically creative. Dense pockets collapsing, stars igniting, exploding, enriching, and collapsing again in rapid succession. The standard timeline allows for this, but not at quite this pace. There's also the possibility that we're misreading the spectral lines. Spectroscopy at extreme distances is challenging. Signals are faint, noise intrudes, dust can alter perceived chemical signatures, but repeated observations strengthen the case. The atomic fingerprints seem genuine, which means the microphysics, fusion rates, cooling efficiencies, molecular formation must have played out with impressive speed. It's humbling, really. You're looking at an object billions of light years away, and the tension might hinge on how effectively hydrogen molecules radiated away energy in the dark ages of the universe. From quarks to quasars. That's the scale of this story. And as you sit there watching spectral lines shift across your screen, you realize that this impossible object doesn't require breaking physics outright. It may simply require acknowledging that the early universe was a far more efficient laboratory than you imagined. Efficient at cooling, efficient at collapsing, efficient at igniting stars. And if the smallest processes unfolded just a little faster, just a little more intensely, then galaxies fully formed, chemically complex, and gravitationally deep could emerge sooner than your tidy charts predicted. The laws of physics remain intact, but their collective choreography may have been more ambitious in those first few 100 million years than anyone expected. And that possibility, subtle, quantum, quietly profound, adds yet another layer to the mystery glowing faintly across the dark. You turn from theory to silicon, because when the universe misbehaves, the first suspect is often not physics. It's your simulation. Modern cosmology lives and breathes inside supercomputers. Enormous numerical simulations, Illustris, Eagle, Millennium, model billions of particles representing dark matter and gas across vast swaths of cosmic time. They start shortly after the Big Bang, input the parameters measured from the cosmic microwave background, and let gravity, hydrodynamics, and feedback physics evolve forward. On screen, filaments form, halos merge, galaxies flicker into existence like embers in a growing fire. It's mesmerizing and reassuring, because when simulations match observations, you feel like you understand something real. But now you load the parameters corresponding to this early epoch and compare outputs. The predicted number density of massive luminous galaxies at redshift this high is low. Not zero, but low. These objects are supposed to be rare, statistical unicorns grazing quietly at the edge of detectability. Yet Webb is spotting candidates with unsettling regularity. Historians still argue whether simulations overestimate the suppressive effects of stellar feedback in early galaxies. If models assume supernovae and radiation blow gas out too efficiently, they may artificially slow star formation in the early universe. Real galaxies might retain more gas, grow faster, and shine brighter than predicted. You tweak a parameter, star formation efficiency up a few percent. Feedback strength down slightly, run again. The structure forms faster, but then something else breaks. Too much efficiency and later epochs become overcrowded with overly massive galaxies. You can't just crank the dial without consequences. Cosmology is a tightly balanced ecosystem of assumptions. You watch the visualization spin, a digital universe blooming inside a machine cooled by industrial fans. Dark matter clumps first, gas falls in, stars ignite, black holes seed and grow. And yet your anomalous galaxy still looks like it's skipping ahead in the script. There's a mainstream fact that often gets overlooked. Simulations cannot resolve every star. They approximate subgrid physics, processes happening below the resolution scale, using statistical prescriptions. It's necessary. Otherwise, modeling even a single galaxy in full detail would take centuries of compute time. But approximations mean uncertainty. Maybe early star clusters formed more coherently than expected. Maybe turbulence cascades differently at primordial metallicities. Maybe magnetic fields played a larger role in channeling gas flows. The simulation doesn't know unless you tell it. There's also cosmic variance, the idea that different regions of the universe can evolve somewhat differently simply due to random initial conditions. If Webb happened to peer into a region that was slightly overdense on large scales, it might naturally host more massive early galaxies. You imagine your simulation box as a tiny cube carved out of the observable universe. Even the largest simulations only sample a fraction of cosmic volume. Rare events might be underrepresented simply because your box isn't big enough. A quirky historical note drifts into your thoughts. In the early days of weather forecasting, primitive models often failed dramatically because they couldn't capture small-scale turbulence. Over time, increased resolution and better parameterizations improved accuracy. The atmosphere didn't change, our models did. Cosmology may be in a similar phase. You increase resolution in a localized region around a high-density peak. Let gravity work harder. Let gas collapse with fewer artificial constraints. The virtual galaxy grows faster. It becomes brighter, closer to what Webb sees. But you're cautious, because if matching one observation requires fine-tuning, you risk overfitting. A model that explains everything perfectly often explains nothing robustly. The Lambda-CDM model has survived decades because it fits a wide range of observations simultaneously: cosmic microwave background anisotropies, large-scale structure, baryon acoustic oscillations, supernova distance measurements. One galaxy, even an impossible-seeming one, doesn't topple that. But multiple? You scroll through early release survey data again? A small but intriguing population of luminous high redshift candidates. Some may turn out to be misidentified. Some may shrink under refined analysis. Still, the trend is there. Your simulations aren't catastrophically wrong. They're just slightly behind, like a weather forecast predicting mild rain when a thunderstorm is already rumbling. Historians still argue whether major theoretical shifts occur when simulations fail dramatically, or when they fail subtly but persistently. Dramatic failure forces revolution. Subtle tension invites gradual refinement. Right now, you're in the subtle phase. The supercomputers hum. Parameter sweeps run overnight. Teams around the world compare outputs. Papers circulate with cautious titles. Tension between observed and predicted early galaxy abundance. No one is panicking, but no one is entirely relaxed either. You sit back and watch the digital cosmos evolve frame by frame. Dark matter threads weaving a web. Gas lighting up nodes. Black holes flickering at centers. It's beautiful and slightly off. The universe Webb is showing you appears just a bit more ambitious than your most advanced computational replicas. Not wildly different, just enough to make you squint. And that's often how discovery begins, not with a shattering contradiction, but with a quiet, persistent mismatch between what your models expect and what reality calmly presents. The simulations keep running, but the data, ancient and indifferent, continues to whisper. Faster, you step back from the glowing simulations and let the bigger questions surface. If the observations hold, if the redshift is right, the luminosity is right, the mass estimates are right, then maybe it's not just a parameter tweak. Maybe it's new physics. Not reckless, tear up the textbook physics, but subtle revisions, extensions, additions to the margins. The standard cosmological model, Lambda-CDM, rests on a few pillars: general relativity, cold dark matter, dark energy in the form of a cosmological constant, that little Greek letter lambda, and initial conditions set by inflation. It has been extraordinarily successful, but it's also incomplete. Dark matter has never been directly detected in a laboratory. Dark energy's nature remains unknown. Inflation's mechanism is still hypothetical. In a sense, cosmology already runs on carefully measured mysteries, so when this early galaxy appears too massive, too bright, too mature, some researchers begin exploring models that gently expand the framework. One mainstream proposal involves early dark energy, a temporary boost in energy density before recombination that slightly alters expansion history. Such models have been explored to address the Hubble tension. If the expansion rate behaved differently in the universe's first few 100,000 years, structure formation timelines could shift subtly. Another idea involves variations in the power spectrum of primordial fluctuations. If small-scale fluctuations were slightly amplified compared to standard predictions, early halos could form more rapidly. This doesn't discard inflation, it refines its output. Historians still argue whether cosmology is approaching a phase like the early 20th century, when classical physics seemed complete, right before quantum mechanics and relativity reshaped everything. Most believe current tensions will resolve within the existing framework, but a few quietly wonder whether a deeper layer awaits. There are also speculative ideas that edge toward the exotic. Primordial black holes, for instance, hypothetical black holes formed not from collapsing stars, but directly from density fluctuations in the very early universe. If even a small fraction of dark matter consisted of such objects, they could serve as oversized seeds for early galaxy formation. Observational constraints are tight, but the possibility remains under investigation. Then there's the notion that dark matter itself might not be entirely cold and collisionless. Some models propose self-interacting dark matter that redistributes energy within halos, potentially enhancing central density growth under certain conditions. None of these ideas are science fiction. They're mathematical possibilities, and that's what makes this moment so quietly thrilling. You imagine cosmologists around the world revisiting equations that have sat comfortably for decades, not discarding them, just nudging them, asking whether a term might be missing, whether a parameter range might be broader than assumed. There's a quirky historical echo here. In the late 19th century, physicists believed they had nearly completed their understanding of nature. Lord Kelvin famously remarked that only two small clouds remained on the horizon of physics. Those two clouds turned out to be the ultraviolet catastrophe and the Michelson-Morley experiment, seeds of quantum mechanics and relativity. Sometimes small clouds grow. Right now, this early galaxy is not a storm. It's a cloud, a luminous one. You trace the consequences in your mind. If early structure formation is more efficient, reionization, the epoch when the first galaxies ionized the intergalactic medium, might have occurred differently than currently modeled. That would subtly affect interpretations of high redshift absorption spectra. If black holes grew faster, gravitational wave event rates at high redshift could shift. If dark matter properties vary, small-scale clustering patterns might deviate in ways future surveys could detect. The beauty of physics is that it's interconnected. Change one thread, and the pattern shifts. You lean forward, imagining the equations of cosmology like a vast tapestry. Most threads are tightly woven and verified, but perhaps in the early corner, those first few 100 million years, the weave is slightly different. Not broken, just different. The cautious language in preprint servers reflects this mood. Possible need for revised star formation efficiency, implications for early halo growth, constraints on non-standard dark matter, models, no headlines screaming apocalypse, just careful curiosity, and you feel it too, that gentle pull of possibility. Because if new physics is required, even in subtle form, it means the universe still has chapters unwritten. It means the map is not complete. It means the night sky, which has guided sailors and poets for millennia, still contains equations waiting to be discovered. You glance once more at the distant glow of the impossible galaxy. It doesn't look rebellious. It looks calm, ancient light, traveling billions of years, simply arriving as it always has. The shock exists only in your interpretation. Perhaps that's the real lesson. The universe doesn't break rules. It reveals where your rules were incomplete. And as the data accumulates, as models adjust and debates unfold, you begin to sense that this discovery, whether it ultimately reshapes cosmology or merely refines it, marks a quiet turning point. Not a collapse of understanding, but an expansion of it. Because when something appears that shouldn't exist, you have two choices: Assume it's an error, or listen carefully. And right now, the cosmos is speaking in a language of ancient photons and improbable maturity. The question is not whether physics survives. It will. The question is how much deeper it becomes. You let the equations rest. You let the simulations quiet. You let Einstein, dark matter, quantum cooling, and supermassive black holes drift gently into the background, like constellations fading at dawn. Because beyond the models and parameters, there is something simpler happening. You're looking at light that left its source more than 13 billion years ago, before Earth formed, before the sun ignited, before there were oceans, trees, or the faint hum of servers analyzing its arrival. That light traveled across expanding space for almost the entire history of the cosmos, never stopping, never tiring, stretching softly as the universe grew. It crossed voids wider than imagination, slipped past clusters of galaxies, curved slightly around invisible wells of dark matter, and finally touched a golden mirror floating quietly a million miles from home, and now it rests in your awareness. Mainstream cosmology tells you the universe began in a hot, dense state and has been expanding ever since. The cosmic microwave background confirms it. The abundance of hydrogen and helium confirms it. The large-scale structure confirms it. Those pillars remain steady, and yet within that steady framework, you have found something impatient. A galaxy that seems older than its age, a black hole that seems heavier than its years, a structure that appears to have grown in fast forward. Historians still argue whether scientific revolutions feel dramatic in the moment or only in hindsight. Often they are quiet at first. A paper here, a tension there, a parameter slightly uncomfortable. Tonight, it is not revolution. It is wonder. You imagine the early universe again, not as a sterile, slow-burning expanse, but as a place of intensity. Regions where matter pooled quickly, where gravity gathered gas with determination, where the first stars ignited in fierce, brilliant bursts, lived briefly, and scattered the ingredients for everything that followed. Perhaps the cosmos was never lazy. Perhaps it was always eager. There's a quirky thought that sometimes drifts through philosophical discussions of cosmology, that the universe in its vastness has tried every possibility somewhere. Given enough space and time, rare configurations become inevitable. Outliers are not violations. They are expressions of scale. Maybe this galaxy is simply one of those expressions. Or maybe it is the edge of a deeper layer of understanding waiting patiently for you to notice. You feel the scale of it now, not intellectually, but gently, like a tide pulling at the edge of your thoughts. The sky above you tonight looks calm. Stars blink softly. The moon drifts in predictable arcs. Everything feels settled, reliable, but out there in the deep past, light still carries surprises. The universe does not rush to explain itself. It unfolds. And sometimes, when you look far enough back, you discover that the beginning was more complex, more energetic, more astonishing than you imagined. You don't need the final answer tonight. You don't need the equations to balance perfectly before you rest. It is enough to know that the cosmos remains alive with mystery, that even after mapping background radiation, detecting gravitational waves, imaging black holes, and launching mirrors of gold into the dark, you are still capable of being surprised. Let that be the comforting part. Not that everything is solved, but that discovery continues, the ancient light keeps arriving. The data keeps whispering, and you, small and warm on a quiet planet, get to listen. So let the galaxy glow softly in your mind now. Let its improbable mass and premature maturity fade into something less alarming and more beautiful. A reminder that the universe is not obligated to match your expectations, only to exist. And as your thoughts slow, imagine those photons still traveling, some still en route from even farther distances, carrying stories not yet told. They will arrive when they arrive. You don't have to chase them. For now, just picture the vast dark, gently expanding, patiently holding galaxies that grew quickly and galaxies that took their time. Picture space-time stretching like a slow breath. In, out. The cosmos is vast enough for anomalies, vast enough for revision, vast enough for you. And as the equations soften and the stars blur into a quiet haze, you can let go of the tension. The impossible object remains out there, luminous and calm. Not a threat, not a crisis. Just a distant glow reminding you that the story of the universe is still being written, one ancient photon at a time. Rest in that thought. Let it settle. The sky is wide. The laws of physics are steady. And somewhere very far away, a galaxy that shouldn't exist continues to shine without apology. You let that quiet settle for a moment. But curiosity has a gentle way of stirring again. Because when conventional explanations feel stretched, older, stranger ideas sometimes drift back into view, not as declarations, but as possibilities. Cosmic strings, for example. Not the kind you untangle from holiday lights, but hypothetical one-dimensional defects in space-time itself. These were proposed in the 1970s and 80s as potential relics of phase transitions in the early universe, moments when fundamental forces separated as temperatures dropped. Think of cracks forming in ice as water freezes. If symmetry-breaking events occurred as predicted by certain grand unified theories, thin, immensely dense filaments of energy could have formed. They would be incredibly narrow subatomic in width, but enormously massive per unit length. A cosmic string stretching across space would curve space-time dramatically around it. Mainstream cosmology has searched for evidence of them, particularly through gravitational lensing signatures or subtle imprints in the cosmic microwave background. So far, nothing definitive has been found. Observations have placed strong limits on their abundance. But the concept lingers. Historians still argue whether cosmic strings were ever a serious contender for explaining large-scale structure formation, or more of a theoretical curiosity that briefly enjoyed the spotlight. Inflationary models largely replace them as the dominant explanation for structure seeds. Yet when something appears unexpectedly massive very early, exotic relics get mentioned again in hushed, cautious tones. You imagine, just for a moment, a region of space threaded by an invisible filament of immense tension. Matter drifting nearby would feel its gravitational pull, gathering along it more efficiently than in surrounding regions. A galaxy forming near such a defect might gain a head start. Is there evidence for that here? Not directly. But the early universe was a high-energy environment where symmetry breaking shaped the forces of nature. The electroweak force separated into electromagnetic and weak forces. The strong force had already decoupled earlier. These transitions weren't gentle, they were transformative. There's also the possibility of other topological defects, domain walls, monopoles, though many of these are strongly constrained because too many would disrupt the universe we observe today. Still, the mere fact that the early cosmos underwent such dramatic changes reminds you that it was not a static backdrop. It was dynamic, energetic, full of shifting rules as temperatures plummeted from incomprehensible extremes. Then there's inflation itself. Inflation proposes that the universe expanded exponentially in a tiny fraction of a second, smoothing out curvature and stretching quantum fluctuations to cosmic scales. But inflation may not have ended uniformly everywhere at exactly the same instant. Some speculative models suggest that slight variations in reheating, the process by which inflation's energy converted into particles, could have produced regions with slightly enhanced densities. Most models predict uniformity within tight constraints. The cosmic microwave background supports that. But again, tight constraints are not zero. You picture the early universe as a landscape just after a storm, mostly smooth, but with occasional deeper puddles where water collected more quickly. Those deeper puddles could become galaxies faster. There's a quirky footnote in cosmological history. Before inflation gained traction, some researchers explored top-down models of structure formation, where enormous structures formed first and fragmented into galaxies. These models fell out of favor because observations supported bottom-up hierarchical formation instead. Yet the tension you're examining tonight faintly echoes those older debates. Not enough to resurrect them fully, just enough to whisper. You also consider cosmic magnetic fields. Observations show that galaxies and clusters contain magnetic fields, but their origin remains partially mysterious. Weak seed fields in the early universe could have influenced gas dynamics during collapse. While unlikely to dominate gravity, they might subtly alter star formation efficiency in specific environments. Speculative? Yes. Impossible? No. The challenge is that any exotic explanation must not disrupt everything else that works so well in cosmology. You can't introduce a cosmic string population large enough to build early galaxies if it simultaneously ruins the cosmic microwave background's uniformity. It's a delicate dance. You sit with that balance. The impossible galaxy doesn't demand cosmic strings. It doesn't require topological defects or radical inflation tweaks. But it opens the door just slightly to the fact that the early universe was a phase transition laboratory of unimaginable scale. And laboratories produce surprises. You imagine space-time cooling, forces separating, particles gaining mass through the Higgs mechanism. The Higgs field itself, confirmed experimentally in 2012 at CERN, permeates all of space, giving fundamental particles their mass. In the early universe, before electroweak symmetry breaking, the rules governing particles were different. Different rules, different behaviors. Perhaps subtle remnants of those transitions influenced structure formation in ways still not fully mapped. Historians still argue whether the early universe was simpler or more complex than today. In one sense, it had fewer elements and fewer structures. In another, it was governed by higher energies and more unified forces, a kind of primordial complexity. The galaxy glowing in Webb's data may not require exotic relics, but its existence reminds you that the early universe was not merely a scaled-down version of today. It was a different regime. And whenever you explore a different regime in physics, extreme temperature, extreme density, extreme energy, you risk encountering phenomena that don't show up under ordinary conditions. So you hold cosmic strings lightly in your thoughts. Not as an answer, not as a conclusion, just as a reminder that the cosmos has a deeper toolbox than your everyday intuition suggests. Out there in the first few 100 million years, forces shifted, fields settled, and matter began its long journey toward complexity. If one region accelerated ahead of schedule, perhaps it did so because of subtle early universe ingredients you have yet to fully decode. The galaxy remains quiet, luminous, unapologetic. And as you continue this journey, the line between mainstream physics and speculative possibility grows softer, not because the rules have failed, but because their early chapters are still being carefully read. You return to the stars themselves, because beneath dark matter scaffolding, beneath inflation and cosmic strings and simulation parameters, there are furnaces, vast, radiant spheres of plasma fusing elements in their cores. And this galaxy seems to have lit an awful lot of them very early. When astronomers analyze distant galaxies, they don't just measure brightness. They examine spectra to determine chemical composition. Specific absorption and emission lines reveal the presence of oxygen, carbon, neon, and other elements forged in stellar cores. The relative abundance of these elements, what astronomers call metallicity, tells a story of prior generations of star formation. In the early universe, metallicity should be extremely low. The first stars formed from pristine hydrogen and helium created in Big Bang nucleosynthesis. Heavier elements had to be built through fusion and dispersed by supernova explosions. Mainstream astrophysics places Big Bang nucleosynthesis within the first 3 minutes of cosmic history, producing roughly 75% hydrogen and 25% helium by mass, with trace lithium. Everything heavier came later, inside stars. That's not speculation. That prediction matches observed primordial abundances remarkably well, which makes this galaxy's apparent enrichment intriguing. Its light suggests not just one generation of stars, but multiple cycles of formation and death. Supernovae would have seeded surrounding gas with heavier elements, enabling more efficient cooling and subsequent star formation. But that takes time, and here's where the tension sharpens. Some early Webb observations hint at galaxies whose metallicity appears surprisingly high for their redshift. Not solar-level rich, but more enriched than expected for their youth. Historians still argue whether metallicity estimates at extreme distances are systematically biased by modeling assumptions. Interpreting faint, redshifted spectral lines is complex. Dust can skew readings, signal noise can masquerade as features. But suppose the enrichment is real. Then the first stars must have formed, exploded, and recycled material with astonishing speed. You picture those primordial giants, hundreds of solar masses burning furiously in the dark. Their lifespans would have been short, perhaps only a few million years. When they died, some would have exploded as pair instability supernovae, completely disrupting themselves and ejecting enormous amounts of heavy elements. Pair instability supernovae are a fascinating prediction of stellar physics. In extremely massive stars, high-energy photons in the core can convert into electron-positron pairs, reducing radiation pressure and triggering catastrophic collapse, followed by explosive runaway. Fusion. The entire star can be obliterated, no black hole left behind. If many such stars formed quickly, they could enrich their surroundings rapidly. But there's another wrinkle. Early galaxies were small and shallow in gravitational terms. Supernova explosions could easily blow enriched gas out of these systems, preventing rapid chemical buildup. Feedback processes were expected to regulate growth, not accelerate it. Yet here you are, looking at evidence that suggests enrichment remained within the system long enough to form successive generations. Maybe early halos were deeper than expected. Maybe star formation occurred in dense pockets shielded from outflows, or maybe the first stars were even more numerous than predicted. There's a quirky anecdote about stellar chemistry. The iron in your blood was forged in a supernova billions of years ago. Carl Sagan loved reminding audiences that we are made of star stuff. Tonight, you're contemplating star stuff being forged far earlier than anticipated. If heavy elements accumulated rapidly, then star formation could transition from massive population 3 stars to smaller population 2 stars sooner. That would stabilize stellar populations and allow galaxies to grow in a more sustained way. You imagine this distant galaxy as a brilliant forge, cycling matter through successive generations at breakneck speed. Stars ignite, explode, enrich, reignite. The tempo feels accelerated. But physics doesn't forbid acceleration. It merely constrains it. There's ongoing scholarly debate about whether early star formation efficiency has been underestimated in models. Observations of nearby starburst galaxies show that under certain conditions, gas can convert into stars with remarkable efficiency. Perhaps primordial conditions favored similar bursts. You scroll through spectral plots again, the oxygen lines, the hydrogen-Balmer series, subtle ratios hinting at ionization states and stellar population ages. It's all faint, all ancient. And yet, encoded in those stretched wavelengths is a story of nuclear alchemy unfolding with urgency. If this galaxy truly contains stars that have already enriched their environment significantly, then cosmic evolution began not with a slow crawl, but with something closer to a sprint. And that doesn't break the laws of physics. It simply suggests that the early universe may have been more industrious than your conservative models allowed. You lean back and let that idea settle. Stars are simple in principle. Gravity compresses gas until fusion ignites. But in aggregate, across billions of years, their collective behavior shapes the universe. If the first stellar generations worked faster, brighter, more intensely, then galaxies could mature sooner. And what seems impossible might instead be a reminder that nature, given dense gas and deep gravity wells, wastes no time. Out there in the young cosmos, furnaces burned. Elements formed, and one galaxy glowing calmly across 13 billion years now hints that those furnaces may have roared to life earlier and more fiercely than anyone expected. You let the stars dim in your imagination and turn towards something even more abstract: time. Because everything in this puzzle, galaxy maturity, black hole growth, chemical enrichment, ultimately rests on one assumption: that cosmic time flows uniformly according to the parameters you've calculated. In cosmology, time isn't measured by wristwatches. It's inferred from expansion. The redshift tells you how much the universe has stretched since the light left its source. Combine that with a model of how expansion evolves, and you convert redshift into age. But that conversion depends on assumptions about the universe's energy content, matter, radiation, dark energy, and how they influence expansion over time. Mainstream cosmology describes expansion using the Friedmann equations derived from general relativity. These equations link the expansion rate to the density of matter and energy. For decades, observations have refined those parameters with impressive precision. Yet even small changes alter timelines. Historians still argue whether cosmic time is best thought of as an emergent property tied to expansion, or whether deeper quantum gravitational frameworks might eventually redefine it. In everyday cosmology, time since the Big Bang is a well-defined quantity. In quantum gravity research, time can become surprisingly slippery. You imagine the early universe ticking forward, not in seconds as you experience them, but in expansion factors. Scale factor increasing, space stretching, density dropping. At redshift 10, the universe was roughly 500 million years old. At redshift 15, closer to 300 million years. These numbers feel concrete, but they are model dependent. If the expansion rate in the early universe were slightly different, perhaps due to early dark energy or additional relativistic particles, the age corresponding to a given redshift could shift subtly, not dramatically, but enough to grant a galaxy an extra 100 million years of growth. In human terms, that's trivial. In cosmic infancy, it's enormous. There's a curious philosophical note here. In 1908, Hermann Minkowski reframed Einstein's relativity by merging space and time into a four-dimensional space-time continuum. Time became another dimension, inseparable from space. Events are coordinates in space-time, not moments floating independently. When you talk about early galaxies, you're really describing events at specific space-time coordinates defined by expansion history. If that history is slightly mischaracterized, then your mapping from redshift to age might be off just enough to ease the tension. There's also the intriguing possibility that time flowed differently in dense early regions due to gravitational time dilation. General relativity tells you that clocks in stronger gravitational fields tick more slowly relative to distant observers. In principle, regions of intense density in the early universe would experience tiny variations in local time. In practice, these effects are far too small to explain large discrepancies in galaxy maturity. Still, it's a humbling reminder. Time itself bends. You think about the Hubble tension again. If local expansion appears faster than early universe measurements predict, perhaps the expansion history isn't perfectly described by a simple cosmological constant. Maybe dark energy evolves subtly over time. If dark energy were slightly weaker in the early universe, matter would dominate more strongly. potentially enhancing structure formation. Conversely, if expansion slowed briefly under certain conditions, gravity would have more opportunity to clump matter quickly. These are delicate adjustments, not radical departures. Cosmologists explore parameter spaces carefully, constrained by supernova data, baryon acoustic oscillations, and cosmic microwave background measurements. Any change must preserve the remarkable consistency of those datasets, but the impossible galaxy nudges at the boundary. It suggests that either formation physics was more efficient, or time, as calculated through expansion, allowed more room than assumed. There's a quirky analogy sometimes used in cosmology. Imagine you're watching a time-lapse video of a plant growing. If the playback speed is slightly off, your interpretation of how fast the plant grew changes. The plant itself didn't change. Your time axis did. You stare at the redshift to age conversion curve again. It's smooth, elegant, based on decades of data, and yet it is a translation, light into time. If that translation is off by even a small percentage at high redshift, early galaxies might not be quite as premature as they appear. You don't leap to rewriting cosmic chronology, but you allow the possibility that the early chapters of the universe may have unfolded on a slightly different tempo than the one currently encoded in your equations. Time in the early cosmos was not experienced by anyone. No observers, no clocks ticking on alien wrists, only expansion, cooling, and collapse. And now, billions of years later, you reconstruct that tempo from ancient photons. If those photons are telling you that structure matured quickly, perhaps the early metronome beat just a little differently. Or perhaps gravity and gas simply danced faster. Either way, you're confronted with the profound reality that time itself in cosmology is not a background constant. It is part of the story. And somewhere in the interplay between expansion and structure, between redshift and age, lies the key to whether this galaxy truly defies expectation or simply reveals that the early universe moved with more urgency than you imagined. You let time stretch gently back into place and shift your attention to something far more terrestrial. Skepticism. Because before rewriting cosmic history, scientists do something beautifully mundane. They check the data again and again and again. Extraordinary claims do not require extraordinary press releases. They require boring, meticulous verification. The first question skeptics ask is simple. Could this be a measurement error? Photometric redshifts, for example, rely on measuring brightness through multiple filters and matching the observed colors to galaxy templates. At extreme distances, faint objects can masquerade as high redshift galaxies when they are actually closer, dust-reddened systems. Dust is the ultimate cosmic trickster. It absorbs blue light and lets red light pass, mimicking the color signature of distant objects. In some cases, what appears to be a galaxy from 13 billion years ago turns out to be a far more ordinary galaxy shrouded in dust, a few billion light years away. So spectroscopy becomes essential. Split the light precisely, identify specific emission or absorption lines, confirm that the wavelength shifts match true cosmological redshift rather than dust effects. In this case, follow-up spectroscopy strengthens the high redshift interpretation. But skeptics aren't done. Gravitational lensing can magnify distant galaxies, making them appear brighter and more massive than they truly are. If a foreground object bends spacetime just right, it can act as a natural telescope. So astronomers search for lensing signatures, distortions, arcs, multiple images. They map foreground mass distributions carefully. So far, no obvious lensing culprit explains away the brightness entirely. Historians still argue whether past astronomical anomalies were resolved by better instruments or better theory. Often, it's the instrument. Early observations of canals on Mars vanished with improved optics. Pulsars were briefly nicknamed LGM for little green men when first discovered in 1967, before their true nature as rotating neutron stars became clear. Nature sometimes imitates mystery until clarity arrives, so teams independently reprocess the data. Different reduction pipelines, different calibration assumptions, different statistical treatments. They ask, could noise fluctuations artificially inflate luminosity estimates? Could background subtraction errors skew results? The margins tighten. The object remains bright. Another skeptical angle, sample bias. Webb's early deep fields target specific regions of the sky. If those regions happen to contain unusually dense patches of the universe, cosmic variance again, you might overestimate how common these early massive galaxies are. It's like surveying one particularly tall forest and concluding that all trees everywhere grow that high. Broader surveys will clarify that. There's also the issue of stellar population modeling. Converting luminosity into stellar mass requires assumptions about the initial mass function, the distribution of star masses at birth. If early stars were systematically more massive than assumed, then mass estimates could be off. Adjust the initial mass function and inferred galaxy mass shifts. But change it too much, and you contradict observations in other epochs. Skepticism isn't resistance to discovery. It's calibration. You imagine astronomers in offices lit by desk lamps rather than cosmic glow, quietly running cross-checks late at night. No dramatic music, just spreadsheets, code, and coffee that's seen better days. They want the anomaly to survive scrutiny, but they also want truth more than headlines. There's a quirky tradition in astronomy of giving early high redshift galaxy candidates dramatic nicknames, some whimsical, some mythological. It's a way of coping with the fact that you're dealing with faint smudges that could upend timelines. Yet behind the nicknames lies discipline. Because if this galaxy turns out to be less extreme than first thought, cosmology breathes easier. And if it survives every skeptical probe, then tension becomes signal. So far, the anomaly persists, not wildly, not explosively, but steadily. Redshift confirmed. Luminosity substantial, structure compact, black hole possibility plausible. Nothing obviously broken in the measurements. Skeptics don't concede defeat. They refine uncertainties. They publish cautionary analyses. They remind everyone that early data releases sometimes overestimate extremes. But even they acknowledge the intriguing pattern emerging from Webb's deeper surveys. You feel that balance now, the steady push and pull between excitement and restraint. Science advances not by leaping at every anomaly, but by patiently filtering noise from truth. Right now, this impossible galaxy sits in that liminal space. Not dismissed, not fully disruptive, just persistent. And as more data arrives, as more regions of the sky are surveyed, the question will sharpen. Is this a rare cosmic overachiever, or the first glimpse of a population your models underestimated? Skepticism will keep you honest, but curiosity keeps you looking. And the galaxy, billions of light years away, continues shining with quiet indifference to the debates unfolding beneath Earth's atmosphere. It doesn't need you to believe in it. It already existed. The real question is whether your understanding will expand to meet it. You feel the skepticism settle into something productive now, not dismissal, not denial, but momentum. Because once an anomaly survives the first rounds of scrutiny, the next phase begins. Verification. Telescopes around the world, on Earth and in orbit, quietly pivot. The James Webb Space Telescope continues gathering deeper exposures, refining spectra, narrowing uncertainties. But it isn't alone. The Atacama Large Millimeter-Submillimeter Array, ALMA, in Chile begins searching for dust and gas signatures at complementary wavelengths. If this galaxy is as massive and chemically enriched as suggested, ALMA should detect emission from ionized carbon or cold molecular gas. Cross-checking across wavelengths is crucial. Different light reveals different layers of truth. The Hubble Space Telescope, though older and less sensitive in the infrared, can still provide optical constraints. Ground-based observatories with adaptive optics systems sharpen their gaze, correcting for atmospheric turbulence in real time. The Very Large Telescope in Chile, Keck Observatory in Hawaii, each adds a piece. Mainstream astronomy thrives on redundancy. If multiple instruments, using different technologies, converge on the same conclusion, confidence grows. Historians still argue whether scientific consensus emerges because evidence accumulates gradually or because a tipping point suddenly crystallizes agreement. In reality, it's often a slow tide, paper by paper, data release by data release. Meanwhile, new surveys expand. The Euclid Space Telescope, launched to map dark matter and dark energy through gravitational lensing and galaxy clustering, adds statistical context. The upcoming Vera C. Rubin Observatory, named after the very astronomer who illuminated dark matter, will conduct the legacy survey of space and time, scanning the entire southern sky repeatedly over a decade. Though optimized for nearer epochs, its vast dataset will inform structure formation models broadly. And then there's the future giant, the Nancy Grace Roman Space Telescope, designed to probe dark energy and exoplanets with wide-field infrared imaging. It will complement Webb's deep but narrow gaze with broader context. You imagine a quiet global choreography unfolding. Telescopes repositioning, observers coordinating proposals, data pipelines humming. No drama, just patience. If more early galaxies of similar mass and brightness appear consistently, the statistical argument strengthens. A single anomaly is interesting. A population is transformative. There's also gravitational wave astronomy entering the scene. If early supermassive black holes grew rapidly, their mergers should generate gravitational waves detectable by future observatories like LISA, the Laser Interferometer Space Antenna, planned for the 2030s. LISA will be sensitive to lower frequency waves produced by massive black hole binaries at high redshift. Imagine confirming early black hole growth, not just with light, but with ripples in space-time itself. The universe offering independent testimony, you scroll through projected observation schedules. Multi-year campaigns, follow-up spectroscopy allocated carefully. Telescope time is precious, like booking a seat at the most exclusive cosmic theater. There's a quirky reality here. Astronomical revolutions often hinge on committees approving observation proposals. The fate of cosmic timelines sometimes rests on a few paragraphs of carefully argued justification. But the excitement is palpable, quietly so, because this is how science handles tension. Not with panic, but with measurement. Each additional data point either nudges the anomaly toward normalcy or reinforces its strangeness. You feel the scale of the effort. Scientists across continents collaborating, debating, refining. Graduate students combing through spectra at 2 a.m. principal investigators drafting cautious abstracts. The galaxy itself doesn't change. Only your certainty does. Historians still argue whether paradigm shifts are recognized immediately by participants or only later by historians. Right now, you're too close to tell. It could resolve into a footnote, a reminder that early estimates overshot reality, or it could become a chapter heading. You imagine, years from now, textbooks describing how early Webb observations revealed unexpectedly mature galaxies, prompting refinements in star formation models and dark matter halo growth rates. Not a collapse of cosmology, a calibration, or perhaps something deeper. For now, the race is not competitive in the dramatic sense. It's collaborative. Telescopes gather light. Analysts extract meaning. Models adjust. The sky, indifferent and vast, continues sending photons, and you sit in this moment between question and answer, between anomaly and explanation. The impossible object still shines, but it no longer feels isolated. It feels like the beginning of a conversation between instruments, between theories, between generations of astronomers. Verification takes time. Ironically, that's the one thing in this story that seems abundant. So you wait not passively, but attentively as more data arrives, because the universe is patient. And if this galaxy truly shouldn't exist, the evidence will either fade under scrutiny or grow impossible to ignore. You let the telescopes hum in the background and allow your mind to wander forward. Because if the data holds, if more early massive galaxies continue to appear, then something subtle but significant happens. Textbooks change, not dramatically, not with fireworks, but quietly, line by line. The Lambda-CDM model would likely remain intact. The Big Bang would not evaporate. The cosmic microwave background would still glow softly in every direction. Dark matter would still sculpt galaxies, but the details of early structure formation would shift. Perhaps star formation efficiency and primordial halos would be revised upward. Perhaps feedback mechanisms would be recalibrated. Maybe the initial mass function for the first stars would broaden. Maybe early dark matter clustering would be modeled with slightly different small-scale behavior. In science, revolutions are rare. Refinements are constant. Historians still argue whether Thomas Kuhn's idea of abrupt paradigm shifts accurately describes most scientific change. In cosmology, it often feels more like erosion than explosion, steady reshaping rather than sudden collapse. If this impossible galaxy becomes part of a pattern, cosmology would absorb it. Graduate lectures would include a new slide, early Webb results and revised high redshift galaxy formation models. Simulation codes would update. Parameter ranges would widen slightly. Review articles would cite 2020's observations as a turning point in understanding cosmic dawn. And future students might find it hard to imagine that anyone once thought early galaxies had to be small and faint. You imagine a classroom decades from now, a professor explaining that in the early 2020s, astronomers were surprised to find mature galaxies at redshifts beyond 10. Students nod casually. Of course they did. Why wouldn't they? That's how knowledge evolves. What once seemed impossible becomes expected. There's a quirky historical parallel in exoplanet science. Before the 1990s, many astronomers assumed planetary systems would resemble our own rocky worlds near the star, gas giants farther out. Then the first exoplanets discovered were hot Jupiters, massive gas giants orbiting scorchingly close to their stars. Theories had to adapt quickly. Now we teach planetary migration as standard. The universe didn't change. Your assumptions did. If early galaxies formed faster than predicted, Cosmology will stretch to accommodate that fact. It already has the flexibility. The equations allow parameter variation. The uncertainties were never zero. You reflect on how much of modern cosmology rests on inference. You cannot watch a galaxy evolve over billions of years. You piece together snapshots at different distances, different times, and assemble a coherent narrative. It's like reconstructing a life story from scattered photographs. If some of those photographs reveal unexpected maturity at young ages, you revise the storyline. But the deeper implications linger. Early galaxy formation influences reionization timing, which affects how transparent the universe became to ultraviolet light. It influences how quickly heavy elements spread, which affects later star and planet formation. It even shapes predictions about the earliest potential habitable environments. Imagine that. If stars and heavy elements formed sooner, the ingredients for rocky planets might have appeared earlier than assumed. Speculative, yes, but connected. You feel a quiet awe now, not alarm, not tension, just appreciation, because the universe is not obligated to be simple. And every time you think you've mapped it fully, it reminds you that scale and time hide complexity beyond intuition. If the textbooks change, it won't mean cosmology failed. It will mean cosmology listened. The impossible object will become an early example cited in review papers. Its designation, whatever alphanumeric string catalogs assign, will appear in footnotes and figure captions. It will join the lineage of discoveries that nudged understanding forward: Hubble's expansion, Rubin's rotation curves, Penzias and Wilson's background radiation, LIGO's gravitational waves. Not overturning everything, but deepening it. You imagine opening a future edition of an astronomy textbook and reading a passage that describes how early Webb observations revealed unexpectedly mature galaxies, prompting a wave of theoretical refinement. And you smile gently at the thought that you were here at the edge of that moment when it was still a question. Because right now it still is. The data is strong but evolving. The debates are active but respectful. The models are strained but flexible. And the universe remains gloriously consistent in one thing: it continues to surprise you. If this galaxy truly shouldn't exist according to older assumptions, then its existence is not a threat. It's an invitation. An invitation to refine, to adjust, to deepen, to let the story grow as vast as the sky itself. You let the future textbooks close softly in your imagination and return, one last time, to the sky. Not the sky of equations and error bars, just the sky. Above you, wherever you are listening from, at whatever local time you shared earlier, the stars look calm, patient, untroubled by redshift tensions or halo concentration parameters. Constellations hold their ancient shapes. The moon follows its quiet path. The night feels settled, and yet hidden within that calm dome are photons that began their journey when the universe was young and unruly. Some of them carry stories that fit neatly into your models. Some of them don't. The galaxy you've been contemplating, too bright, too massive, too mature, still shines across billions of light years. It does not care whether it aligns with Lambda-CDM or stretches star formation efficiency curves. It simply exists at its space-time coordinate, emitting light according to the same physical laws that govern your sun. Mainstream cosmology remains strong. The Big Bang is not in crisis. Dark matter still explains rotation curves and lensing. General relativity still predicts gravitational waves with astonishing precision. And yet, historians still argue whether the most important scientific discoveries are those that confirm what you expect or those that gently unsettle it. This object unsettles gently. It suggests that the early universe may have been more industrious, more efficient, more dynamically creative than your conservative assumptions allowed. Perhaps gravity gathered matter faster in rare pockets. Perhaps gas cooled more effectively in primordial conditions. Perhaps black hole seeds were larger than anticipated. Perhaps your translation from redshift to time needs slight refinement. Or perhaps it is simply a statistical outlier, a cosmic overachiever born from a particularly tall ripple in the primordial plasma. All of these possibilities fit within physics. None require abandoning the framework. They require listening more closely. There's a quiet humility in that. For centuries, humanity assumed the universe was static. Then it expanded. You assumed galaxies were singular islands. Then you discovered billions. You thought black holes were mathematical curiosities. Now you photograph their shadows. Each time the cosmos widened, never maliciously, just honestly. The phrase "shouldn't exist" is always temporary. It really means doesn't fit what we currently expect. And expectation is a moving target. You imagine those ancient photons leaving their galaxy when it was still young, perhaps already structured, perhaps already hosting a massive central black hole long before Earth coalesced from dust. They traveled while continents formed, while life crawled from oceans, while mammals evolved, while humans learned to map the stars. And now, in this quiet era of silicon detectors and space telescopes parked at gravitational balance points, you receive them. You measure, you question, you adjust. That is the rhythm of science, not certainty, not collapse. Adjustment. You feel the scale again, not overwhelming, just expansive. The universe is 13.8 billion years old, and you are catching light from near its dawn. If that dawn turns out to have been brighter and busier than anticipated, that is not a failure. It is richness. And somewhere beyond even this galaxy, there are others, fainter, farther, still sending their messages. Some will confirm your models beautifully. Some will nudge them. A few may someday force deeper change, but tonight, you don't need to resolve it. You can simply appreciate the fact that even now, even with all your instruments and equations, the cosmos retains the power to surprise. That is not instability. That is vitality. The impossible object continues to shine, and you, small beneath the sky, continue to learn. Let that be enough. Let the questions soften. Let the equations fade into distant constellations of symbols. Picture space-time stretching gently, galaxies drifting apart like embers carried on a slow cosmic wind. Somewhere in that vastness, a galaxy that once seemed out of place now feels like part of a larger, still unfolding story. And you are here for it. Rest in that thought. The universe is not finished revealing itself, and neither are you finished discovering it.